we are now recording. So, let's talk about just a few things. Number one, I think I mentioned this before, and I think you probably should have seen it in your emails. They are doing fire alarm testing on this campus through tomorrow. Okay? So if you hear an alarm go off and you don't see or smell smoke or fire or smell smoke, or you don't hear someone going up and down saying, this is not a test, this is a reality here, that we do have a fire, we just don't move. This is not either a test or a drill. A drill or an actual fire. It's just testing the system. So don't worry about it if you hear the alarms go off, unless you have some reason to know it is real. Okay, so that's that for today. Now, let me hit school stuff first. Next week is Cougar Connection Week. Yes?
I was wondering if I can make an announcement.
Sure, go ahead.
How y'all doing? Mr. Fowler has been mentioning for the past about 2 weeks now.
Something like that.
Yeah, about 2 weeks now. Cougar Connection Week is upon us. Next week, as he said, next week is Cougar Connection Week. On Monday, we have the Get On Board / Volunteer Fair at Birmingham from 11 to 1 outside the library there. The Bessemer campus has the Constitution Day seminar on this campus at about, 12 o'clock? Am I right, D? Yeah, 12 o'clock.
Yeah, 12 to 1.
All right, thanks. On Tuesday, we have the Get On Board / Volunteer Fair on this campus out at the Quad from 11 to 1. The Constitution Day seminar will be at the Bessemer campus, down at the Thumb Catlin Auditorium. Yeah, Birmingham campus. The Constitution Day seminar for this campus will be in the faculty dining area. On Wednesday, there's an HIV seminar going on this campus in room 105 in building A from 1 to 2, I believe.
Yeah.
The SGA is doing like a serve day thing down at the Birmingham campus at around 3 p.m. On Thursday, the three of the student organizations that I know of is having their induction ceremonies. SGA, Ambassadors, and PTK, aka Phi Theta Kappa. The induction ceremony will be going on at 1 p.m. We don't know what time it is. Me and Demetrius will be at that event. We're getting inducted for the third time. Right, D?
And last but not least, we have a pool party at the Birmingham campus around the gym. It will start at 4 p.m. and it will end at 6 p.m. So if you have any free time or time you can make up, come to support the event we have next week. And another thing, if I get on board day, that's a good opportunity for you to talk with our state organizations to try to join to get opportunity, or if you look for a new job, anything, there'll be some opportunity there at Get On Board Day.
And there's also going to be some student organizations on those days. SGA, Ambassadors, Student Support Services, STEM, the Athletics, Fine Arts, pretty much every organization that the school has will be at Get On Board / Volunteer Fair. Thank you for your time.
All right, thank you. Well done, too.
Thanks.
Okay. So that's campus-wide stuff, and that's going on next week. And here's Justin. Let's talk about this class a little bit. We're almost through with Chapter 17. We will finish it very soon, and then we will move on to Chapter 18. Ramifications of that. That means at 3:45, we will move to go to a lab. I don't know exactly precisely which lab we're going to yet. If there's no orientation room class going on in room 256, that's my preference. It's close, and we can get there easily. So that is my first choice. I just don't know for certain if there's an orientation class in there today at that time. I just stopped by on the way up, and the people that are in there said, no, they're going to be going by 2, which I figured to be the case. I thought someone might know if there's something later. It seems like there's usually someone down there when I finish this class, so it may not be available to us. If it's not, then we'll go down this half flight of stairs, and at the base of that, go up one more flight, and room 361 is right at the top of the stairs there, and that's a room we can go to. A little bit maybe better room will be across the hall, but Mr. Armbruster didn't know yesterday if there was a class in there. He knows the one where his office is, 361, will be available. He said the one across the hall might be a better room for us, but it might be being used. So if we can't go to 256, we'll go up either to 360 or 361 up on the 3rd floor. Okay, so that'll be the lab for this chapter, 17, though we'll have started in 18 already by then. All right. Then, next ramification for that is, it means on Thursday, the last 30 minutes will be our test on chapter 17. So know that as well. Okay. Be ready. Formula equation sheet, whatever you want to bring, that will be Thursday. Now, if we finish, and there's a real good chance we'll do 18, since we're going to get started on it relatively soon today, but going to stop for lab, and then we'll have 2.5 hours on Thursday. There's a real good chance we'll finish 18 in time, and its lab will be the 2 hours before the test. So we may have 2 hours of class, 2 hours lab, and 30 minutes of test. So that's the rest of this week. Now, I was finally able to talk with someone over at Sanford. I had left so many messages over so many days, never got a call back as far as I could tell. And when I talked with him yesterday, it was like it was news to him. So evidently he hadn't heard any of my messages. But he said this week is booked solid. He can't fit us in. He said next week he thinks it's going to be full both days. But then the following week, I know that's getting late in the term, but that'll be the 25th. The 25th of September, we've got it. And what we'll do is leave here right at 1:15. So everybody needs to be here. If you want to ride in the van, I haven't gotten it yet, but I think it won't be any problem getting it this far in advance. So if I can get the van, I think, how many does it hold? Do you know?
I don't know. I never voted in that van.
Oh, you haven't. I think it's called a 15-passenger van, but the insurance won't cover that many people. So it's limited to how many people can ride. So if anyone can drive and maybe take another person or two with you, we can get there with the van and a few others. But
I'll ride in the van.
Okay.
I got my word on that.
Okay. So we'll get as many as we can in the van, and then if someone else. For some of you, it might be more convenient to go straight to Sanford rather than driving here and then driving back to Sanford, if you live that way. So if that's the case, then that will work out well too.
You said that for next week we have to be here at what time? Normal class time.
Okay. It's normal class time, 1:15. That'll be on the 25th I'm talking about.
On the 25th?
Yeah, that's 2 weeks from today.
So that means what time do I have to be here for the week after the next?
Okay. Yeah, week after next. Well, you have to be here every day. We have class every Tuesday and Thursday. No, right. Yeah, but the field trip will be on the 25th, and those who do want to ride on the van in the van will need to be here at 1:15 so we can get going and get there in time. DeAndre's here. He'll have us for, I think he said about an hour and a half. Okay, so that'll be from 2 to 3:30 approximately, and then we'll be coming back here to this campus, and we'll finish up our time together here. Okay, so if you do meet us there, plan to come on here, maybe give some people a ride if they need it, and but that will be on the 25th, and that will be the planetarium visit. Won't be long after that. We'll be scheduling the one for the weather too. So we're running out of term there really quickly. I'm sorry? No, the second one will be, if we can schedule it, it will be at Channel 13 Weather. The Channel 13, News 13,
WBT.
Alabama 13. That's at Vulcan Park, right near Vulcan Park.
Last Tuesday, James Mann was at my job.
Yeah, I heard someone say that. And what was your job?
Oh, yeah,
What's that?
Alabama.
Oh, really? Okay. So he was out there then. Yeah, well, Jerry Tracy hosts us at Channel 13, so, but yeah, same type
And I
deal.
think he was probably there because Hurricane Florence is approaching was about to approach the Carolinas, and
Right.
they're going to need all the help they can get regarding power when it gets knocked out, since Florence is now officially a Category 4.
4, okay. I had heard that she was 4. I heard there was a chance she could move to 5, but I know she's a 4 right now. So, and she, from what they say, she's huge.
I
It's
think
just don't-
Florence
Just
is
from
like
outer space,
heat.
she's like,
Huh?
just from outer space, it's like really big.
Yeah. So it's going to hit and affect a lot of the eastern seaboard from Charleston north, I think, or so, up to maybe even as far as Maryland. So that's a huge area that can be
Does
involved.
hurricanes also get covered in meteorology?
Yeah, we'll talk about that in that's the same chapter, the weather chapter,
Yeah.
weather and climate.
Just want to make sure.
Okay. All right. So that's how things are lining up for the course. Any questions before we get started on today? Okay, let's get the current slide up. I do have the screencast-o-matic on. Okay. We, in some senses, saw in the astronomy thing how stars form, live their lives, explode, come back, send out clouds of gases into space, and then form again. It's sort of like a cycle. Just about all of nature is like a cycle, including the rocks. This is the rock cycle. Don't you think geology rocks? Never mind, that's another question. Okay. Rocks are transformed into new types of rocks by the Earth's interior and exterior dynamical processes. And again, dynamical means changing, active. Okay? We have the moving continents. We call it plate tectonics. That's the next chapter. We have seas advancing and seas retreating constantly. Those are forces. We have weathered and eroded rock, or the rocks are weathered and eroded by wind, by rain, and much slower, by glaciers and other things. We'll talk about those in another chapter. Okay, but all this stuff is going on constantly. Now, it's going on slowly. Certainly, continents don't move very fast. Seas advancing and retreating, that's fairly slow. And the weathering and eroding of rocks by wind and rain, very, very slow, but it's always happening. Okay? So we have rocks being transformed all the time. And here is a rather weird-looking diagram, but it really pictures it incredibly well. Now, where do you think we ought to start? You pick a place. Say again? Sediments? Okay. Well, you have to know where the sediments came from. So let's back up just a little bit from sediments. How about here? How about magma? Okay, it's not rock yet, certainly. That's liquid, right? Hot liquid. Okay? So this is the only thing on here that's not a rock. Will soon be a rock, but it's not a rock yet. And we're going to come back to it as well. Now, when magma cools, what kind of rock do we have? Igneous rock and only igneous rock. Okay? So magma, as it cools, it solidifies and becomes igneous rock. Now, the rate at which it cools, you know, how rapidly or slowly it cools, that determines what kind of igneous rock we have. Okay? A slow cool is going to be large crystal size. We call it intrusive igneous rock. Rapid cool, like on the surface, that would be extrusive igneous rock. So that determines texture and other things such as that. Also, how deep it cools. Some of the rocks, the minerals, will come out at very high temperatures, very deep, and others come out later and later and later at cooler and cooler temperatures. So that also determines the composition of the rocks. But those are all igneous rocks. Okay? Now, what happens to igneous rock? Well, this weather and eroding by wind, by water, and everything else will break down these igneous rock into smaller pieces. Now, the pieces could be as big as boulders. Well, those are just big chunks of rock, okay? It could be gravel, okay? It could be sands. It could be silts. It could be clays. But they are weathered away by wind and by water and other things as well. We'll get to that in another chapter. Those sediments then, that's where you wanted to start before, they start settling out. They sediment and get piled on deeper and deeper and deeper. With increased temperatures and increased pressures, that process starts the lithification process, and that forms new rock, and that's called sedimentary rock. Okay? Now, they're not all from igneous. Some of them from igneous. The sedimentary rock can be clastic, which means particles. Big particles like gravel would be, just went blank. Breccia and conglomerate. Okay. Those are the two types with big chunks like gravel. Sand would be sandstone. Silts would be siltstone, sometimes called mudstone, and clays would be claystone, sometimes called mudstone. Well, guess what? These sedimentary rocks also break down and go back to being sediments again. So there's a really short cycle in here sometimes between sedimentary rocks going back to sediment. Or if those sedimentary rocks go under more pressure, higher temperatures, then they can change the crystal structure and metamorphosize into a different kind of rock, metamorphic rock. Metamorphosis is change, big time change. Okay. Same thing here though. Some of these igneous rocks could get piled on deeper and deeper, more pressure, more temperature, and these could become metamorphic rocks if that same metamorphosis happens to igneous rock. But what happens to metamorphic rock? It either breaks down, weather, wind, rain, and it goes back to being sedimentary rock, and it starts that process again. Or if it has more heat, more pressure, it could change a time or two to different kinds of metamorphic rock. But at some point, if the temperature gets too hot, what happens? It melts. And once it melts, it goes back to being magma, and the magma is going to become igneous rock again. Okay? There's the rock cycle. Magma to igneous rock to sedimentary rock to metamorphic rock to magma, or igneous rock, magma to igneous rock to metamorphic rock to magma, okay? Or igneous rock to metamorphic rock to sedimentary rock from metamorphic rock to magma. I mean, it can go around and around, take any of these paths it wants to in any way, shape, or form. That's the rock cycle. Almost like it's a wheel within a wheel within a wheel within a wheel. Okay. Quite a cycle. And I think that may be the last slide.
It is.
Okay. Now, You know what I'm going to say next. Nothing replaces reading the chapter. No, not a thing. There's some great pictures in here too, well worth your read just to see those. Some of these we've seen and pointed out before. I wish I'd have brought one thing from home. It looks just like that piece of marble, and I don't have any idea how it wound up in our yard. But I'll try to bring that some other time. There is a summary at the end of the chapter. This is a little bit maybe shorter than some, but it's pretty important. And again, the important terms are usually put in italics, so pay attention to those. And then the key terms are also highlighted under key terms. And again, the list may be a little bit shorter, maybe about normal to shorter than most. They list them alphabetically, but they have the page number where the term either first was mentioned or defined. So you can do that. But then, applying the concepts, to me, just about the most important study guide, I would say, that you have, study tool. These are multiple choice questions. Most, not all, but most of your questions will be multiple choice. And even those that aren't, you can probably find things, the same concepts in these multiple choice questions. They have the answers provided. This chapter only has 43, which is, again, a few fewer than maybe the average, but there's still good questions there. And you won't see any of these precisely on the test, but you'll see the same topic approached from a different angle. Okay? Then, questions for thought. Wow, 19 in this chapter. That's probably more than normal. For further analysis, you got 4, maybe normal a bit on the short side. There is an invitation to inquiry, which you can read if you'd like. Not very long. And then the parallel exercises, which mostly are sort of some of the made-up problems. But some of them are pretty good, but a lot of them are based on things on the first half of the book, which I don't think anyone in here has had the Physical Science 2 yet. Okay, some of you may be going to take it the second half. Then those questions would have made more sense. So any questions on chapter 17? 17 lab will be today. And by the way, let me talk a little bit about the lab. It's strictly, the reason we're going to another room is strictly a computer lab. So if you got laptops, you certainly can use those. And then there'll be computers in the lab we go to. Even the backup lab, which is up in the 361, it doesn't have quite enough computers for everybody, but not everybody's here today. And several of you have your own computers, so we may not need any more than are in that lab. But if we do, we'll do it. But it's a lab. You can work together in teams of 2 or 3 or something like that. So everybody doesn't have to have a computer as long as everyone's contributing. All right. So any questions on today's lab? But today's lab is strictly pretty much a computer lab. And I'm going to get, here's the reason I want it downstairs, have a bunch of rock samples, and I'd like to just be able to go across the hall with them rather than haul them up and downstairs. But I'll haul them up and downstairs if we need to. Was there a question? Oh, shucks, I guess so. Okay. Some people, I think, were wanting to do some makeup testing and things, weren't they? So perhaps you might have something else to do after, or you can do it later. Okay? Now, that reminded me of something, and now it flew the coop. Oh yeah, that's what it is. I do this every now and then. This sounds like a good lead-in for it. This class is ahead of most. Of course, it's a mini-term class, so it should be ahead of them. And having 5 papers in among the, what are we down to? 16 students in the class. 5 have already turned in research papers. Fantastic. That's almost a third of the class. Keep them coming, folks. Okay. But the other things are not coming in as fast. Lab 1, I'm still missing 1, 2, 3, 4, 5, 6 lab 1s. Test 1, missing 1, 2, 3. Lab 2, 1, 2, 3, 4. Test 2, 1, 2, 3, 4. Lab 3 y'all are working on, aren't you? Moon Lab? Yes, good deal. Test 3 missing 1, 2, 3, 4, 5. And then that's up to where we are today. So please, folks, if you got labs out, get them in. Except the Moon Lab, that's going to take you a little bit longer to do probably. And if you got tests you're missing, please get those caught up. I want to return these to you so they make more sense to you. And also so I don't have to carry them around anymore. Okay, so please get your caught up as soon as you can. All right, any questions? Let's move on then to chapter 18. And we've already been talking about 18 in many ways. And all these chapters, from these, especially these 4 chapters in what I call the geology part, the earth science part, they all mix and mingle like crazy. And even among the astronomy type things, when we talked about the earth and how it's put together, that mixes and mingles with these well. So when we're doing the labs, today's lab very much is on chapter 17. Very same things we talked about in chapter 17 we're going to do. But from now on, the labs will go forward, they'll go back, they'll do things. We'll be talking about stuff. You'll have one lab coming up sometime on latitude and longitude, which we talked about back in chapter 16, okay? But we'll be, so the labs sort of go all over the place, but they all tie together fairly well. Okay, so let's get going on chapter 18. Plate tectonics, okay? What does that mean to you, plate tectonics? What?
What we said on, I
Huh?
guess. We said cracks in the earth.
Oh, yeah. Okay, not a bad description. That the surface of the earth is really big old plates. They can't go far, but they do get hung up on each other and then release suddenly and things. That's the cause for earthquakes. Can be the cause contribute to volcanic activity. It changes the Earth's surface in many ways. It was influential in the rock cycle, the pressures and the temperatures. So yeah, that's what we're talking about in this chapter. An earlier version of plate tectonics, a theory, anyone remember what that was called? It was called continental drift, where they talked about the continents moving further apart from each other. Of course, if anything's moving further apart, something else moving closer together. Can't have it. We were fixed size. We can't be expanding any. So So that was the old name for what we now call plate tectonics. Okay, here is the core concept, found on your page 458 or so in your text. Okay, which is pretty close to the same figure you saw, a similar figure to this one here. Okay. Earth has an internal structure, and we'll talk about that first, early on. And guess what? Cycles materials. Okay, just talked about the rock cycle. Cycles materials between the surface and the interior. And we were just basically describing that in the rock cycle. Okay. Now this figure here we're going to see in more detail, and a little bit bigger, coming up toward the end of the chapter. But this shows some of the major plates. We, of course, live on the North American plate, which doesn't just include North America. It includes the northwestern quadrant of the Atlantic Ocean. It's all in the North American plate. There's a little plate down here called the Caribbean plate that includes much of the Caribbean islands. Father Islands down there, a little bit of South America, a little bit of Central America. And if you think about it, you've probably heard of volcanic or earthquake activities going on in some of those areas. There's the South American plate, which again is South America, plus the southwestern quadrant of the Atlantic Ocean. That's the South American plate. There's a little plate down here that they don't identify. I don't know if that's an error or if there is a little plate they just don't have a name for it. There's on the west side of South America, there's the Nazca plate, which is jamming into this and creating, and yes.
Ain't California on another plate in North America?
Yeah, its boundary is on between the Pacific plate and the North American plate. That's a plate boundary. We'll be talking about the significance of plate boundaries. There's one down here between the Nazca plate and the South American plate. Okay? Big old plate here, the Pacific plate, but it's not all the Pacific, just parts of it.
Isn't that called something?
What's that?
That area along the edge of the plate, isn't that called something?
It's sometimes called the boundary area. They're called, there is a term, I think. I'm going blank. What you may be thinking of the San Andreas Fault. That's the line, fault line between that. We'll talk about what a fault is and other things like that too. There's a tiny little plate up here called the Juan de Fuca plate, which has a pretty big significance for how tiny the plate is. Okay? One thing you might note too is a lot of these boundaries that you're talking about, they almost define arcs of islands. Okay? And especially these out in the middle of the oceans here, they define there. For instance, New Zealand forms the boundary here. There's a reason for that. That's why New Zealand exists. Up here, here's the country Iceland, right on that boundary. That's why Iceland is there, because it's right on a plate boundary. Okay. Here's the Philippine plate. That's responsible for the Philippine Islands being there, by and large. I don't know if you ever thought of it, there's the Eurasian plate, Europe and Asia all together. Huge plate. Okay? But part of Asia is not on that. India is not, for instance. It's in the Indian-Australian plate, which is a lot of it's water, underwater, but parts of it are, you never would have thought, or I wouldn't have thought, Australia and India would be together and on a different plate from the Philippines or Malaysia and Indonesia or any of that. You have the African plate here, the Arabian plate. I think I've covered most of them. Okay, so we'll get a lot more detail on that later. So let's look at a history of the Earth's interior. Now this is starting on this is section 18.1 on page 459. As we've said probably several times now, Earth was formed approximately 4.6 billion years ago in the solar nebula. Okay? We say the sun is about 5 billion years old, so while it was still forming, we weren't quite together yet. Okay? That's the solar nebula, when the sun was just coming together and becoming a sun and stuff and blowing up and everything was unstable. That's when the Earth basically formed. Early Earth had a molten surface. Okay? I mean, the surface of the Earth was liquid. It was magma or lava or whatever you want to call it, because that whole process of splitting off from the sun and stuff, that was a very hot, intensive time. And you're just being banged by other materials out there, bombarding materials. You had a lot of high radioactivity out there, so that was keeping things heated up. So we had a molten surface at that time. Now, going back to the last chapter, chapter before last, that may have been when we had some huge collision with something and it broke off part of the moon. If we were basically a ball of hot molten rock, it would, if we got hit by something, it would be fairly easy for a splatter of that to go off and become the moon. And perhaps that's what happened. Okay? Now, over time, though, and when we're talking time, these are long periods of time, the surface did cool and crystallize. And what did molten rock crystallizing become? Igneous rock. So that's how they say at one time all the rock was igneous rock. Okay? There weren't any metamorphic and sedimentary. When we first cooled, we were all igneous rock. Okay? Now, again, remember I said radioactive. Heat was going on. The heat accumulated from that radioactive decay led to a second melting, this time of the interior. Okay, you would have thought it would have been melted first, and maybe it was, but maybe it was more solid. But now the heat is sort of gathering on the inside. So much of our interior was molten. Okay, still is, by the way. The melting occurred in pockets, not throughout the interior. Okay, and we're going to name, in some senses, some of those pockets a little bit later. I'll try to remember to say this is what we're talking about, if I can remember to backtrack and do that. Okay, what happens in this process is what they call differentiation. Okay, the melting and the gravitational settling of the heavier metals, as they melt, heavier stuff sinks faster than lighter stuff. The lighter stuff moves up, the heavier stuff down. So that's where you get some of this differentiation, which produces the Earth's present stratified structure. Now, what do we mean by that? We'll see the Earth structure a little bit later, but your heavier stuff, mostly your iron and your nickel, is interior, and then the lighter stuff, like the quartzy materials, the non-ferromagnesium silicates, are more toward the surface because they're lighter. Okay. Now, part of that differentiation, we came up with two cores. Okay, the innermost core is solid. And I think the only reason it's solid, there's so much pressure on it, it just forces things together into a solid. But the outer part is still molten, and that's mostly iron material. The innermost part is probably mostly iron material. No one's been there to tell, but it seems like it. The outer part of the core, the molten part, is mostly iron. A fair amount of nickel and stuff too. And then, as you move on further out, you get lower quantities of iron and greater quantities of silicon. Now, conditions at the Earth's center, the pressure, about 3.5 million atmospheres. Now, I think we talked about before, you got 1 atmosphere of pressure over you here. That's about 14.7 pounds for every square inch of your body, or of anything, okay? 14.7 pounds for every square inch. If I think about how many square inches are on my body, I'm holding up my 2 thumbs, that's about a square inch, the area covered by my top joint of my 2 thumbs together. It's about a square inch. There's a lot of those covering my body, and that means that much force is on me. That's 1 atmosphere of pressure. And as I said before, if you go down 10 meters, which would be like a 3-story building, the other part of this building, where the business stuff is up top, that's a 3-story building. Because I'm about 2 meters, that's another meter, three stories. If you have another meter somewhere in there between the stories and stuff, you will have that. That's another atmosphere of pressure. Okay, that's underwater now. Go down another 10 meters and you get another atmosphere. You're up to 3 now. Go down another 10 meters and of water and you got that. Well, you can go down lots of 10 meters, 400, 500, 600 sets of 10 meters, and add a lot of atmospheres that way. But at the center, 3.5 million atmospheres, that's a lot. Well, that's because the mantle, and we'll talk about this later, and the other things are so incredibly heavy, and the gravitational compression of that really builds up the pressure. The temperature down there, 6,000 degrees Celsius. Now remember, it's nowhere close to hot enough for fusion to happen, and there's not many fusion materials down there, but that is hot. That is really, really hot. That's at the Earth set, which is largely solid, and even at those temperatures, just because of all that pressure pushing in. Okay, people are still writing. Now, one question that comes to my mind says history of Earth's interior and everything we have here is how things have changed in big ways over time. Are they still changing in big ways, or are we sort of stabilized and now it's just little changes, temporary changes? It's a very good question. I don't know the answer to it. I would think we're probably fairly stable now, but things are still dynamic and changing. The other issue is, back at our beginning, since we came from radioactive explosions of the sun, it seemed like everything would have been fairly radioactive, and that's why there was a long time before there was any life on the planet. Enormously long periods of time. And then that happened pretty much slowly. Well, then my question is the radioactivity still decreasing? If it is, it's at such a slow rate we don't notice it. But that, to me, is an important issue, is at some point we're not going to have that much radioactive material here, which may have implications for atomic energy, but I don't know. All right, everybody finished? I was just sort of shooting the breeze until everybody got finished. So let's look at evidence of the Earth's internal structure. Okay? One bit of evidence is we are a magnet. The Earth acts like a huge magnet. That's why we can have a compass and it's going to point north, because the Earth acts like a magnet. Since we call that point on the compass needle a north pole, well, that means north on the Earth must be a south pole, because north poles are attracted to south poles, which is rather bizarre. So I like to call that a north-seeking pole on the compass, which means seeking our north pole. But that sort of semantics. Okay? So the fact we have an Earth magnetic field, that we are a big magnet, that means, well, you haven't had the earlier part of the book, but let me tell you a key concept that you would find in the Electricity and Magnetism chapter, which I think is chapter 6 or somewhere back there. What creates a magnetic field is a moving charge. Moving charge induces a magnetic field. So therefore, for us to have a magnetic field, we have to have moving charges somewhere on our interior. Well, how would these charges be moving except that there would be stratification? There must be some liquid part and some solid part, and they're bending across and not a smooth boundary either, and they are constantly knocking into each other and knocking off electrons, which creates an electron moving charge, which induces a magnetic field. So that's one bit of evidence. If we didn't have a magnetic field, you would think we'd all be stable inside. We do have a magnetic field, things are going to change. Gravity effects. Now, we all have gravity, we know that. Well, sometimes I think some of the climate deniers probably don't believe in gravity either, because all the science points to climate change, but they don't believe that, so why should they believe in gravity? I mean, why not? Never mind. Okay, that was political. Okay. The gravity effects. If we were all made out of silicates, we'd be a much lighter planet. And a much lighter planet would not have a stronger gravitational field. So we do know something about the effects of gravity that we have to know there's a lot denser down there than it is up here. Otherwise, we wouldn't have. We know enough of the science to know. So gravity effects also tell us something about the Earth's internal structure. Heat flow. Okay? Now, the obvious thing for heat flow to me is movement of magma up and down, throughout the thing. That's one form, but just the heat moving through rock and the heat moving through thing, there's got to be a better conduit than just rock. That indicates there's some internal structure that is contributing to that heat flow. Now, this is the one that probably tells us the most. Vibrations in the earth. What do we call vibrations in the earth? Earthquakes, okay? When the earth vibrates. When it does, and it does, just recently, where was the last one? There was one in Japan. Say?
Yeah, the one in Japan about a few weeks ago.
Yeah, just not long ago at all. And if I'm not mistaken, that couldn't have been too far from the one that created the nuclear close to disaster.
Yeah, tsunami.
Yeah, the tsunami that caused that. And that was caused by an earthquake. And that wasn't that many years ago. And who was asking about the boundaries? I think it was Ancesia. It's me. Yeah, this is where the boundaries are where the action are, and that's where most of the earthquakes occur. Okay? Well, what do these earthquakes, these vibrations of the earth, they create what we call seismic waves. And there's at least 3 different forms of seismic waves. We'll be talking about those in a later section today. Some today and some Thursday. Now, the seismic waves radiate outward from the earthquakes. Wherever the earthquakes were, they radiate outwards. Now, this is a strange line to put in here, but it's sort of true. And earthquakes release a lot of energy. The closest thing that man does to approximating that, nuclear reactions. That means nuclear explosions, not just reactions. Those are pretty controlled. Nuclear explosions. So guess what? Anytime Pakistan, North Korea, anybody decides to detonate, to test a nuclear weapon, everybody in the world knows within a fairly short time, because the seismic waves are also noted from nuclear explosions. So you can run, but you can't hide. And guess what? The thing of tsunamis that we mentioned already today, and we'll mention again in a later chapter, and seismic activity, those are 2 of the best samples of international cooperation we have. Every country in the world that borders in a big body of water has tsunami detection around it, and they share it with everybody. Even their biggest enemies, they share it with everybody. It's scientific, it's not political. And the other thing is these seismic waves. Every country in the world has places they measure seismic activity, and it's all shared without modification, shared with everybody. So everyone knows if there's a nuclear explosion. Whether it's been announced or not, everybody is going to know pretty soon. So let's look at these seismic waves, and here are the 3 types, and we'll go through these in some detail. The first are called the P waves, and there's several names you can associate with the P. The first is pressure wave, and as they say, longitudinal and compression, but think of pressure wave. Okay? Right now, I'm emitting pressure waves. If you can hear me, you're receiving pressure waves. Because when I talk, or you talk, or anyone talks, you're sending out in what they call, you're compressing air molecules, and then they're rarefacting, meaning spreading apart, and that compression and rarefaction, that's what makes sound. Okay? So if you're hearing this, which I assume most of you are receiving pressure waves. So P wave, now that's not seismic, but it's like a seismic wave. The seismic waves are their fastest, the P waves are your fastest waves. So keep that in mind. We'll be talking about that late in the chapter. And the other thing about P waves, they move through surface rocks and interior solid and liquid materials. Okay? So the other name, I think it's really where the P comes from, primary waves. Pressure waves, yes. Primary waves is the better. Those are your P waves. They're the fastest, and they move through all materials. Rocks, solids, and liquids. Okay? That's the important thing about P waves, one of the important waves. The fastest, they're compressional waves, and they move both through solids and liquid materials. And if you think about it, a lot of the Earth is liquid. It's magma. Okay? And they move through that with no problem. All right. Secondly, are your S waves. Okay? S meaning secondary waves. Or S meaning shear waves. Okay. Now, I gave you an example of a pressure wave, sound waves. Okay. Here's my favorite example of a transverse wave. I can remember as a kid, I don't know why this is something I still remember, but I remember just being fascinated by it. When we were doing something with a hose stretched across the yard. I loved to get the end of the hose and yank it up and yank it down real fast. And you saw this snake-like or almost like a Loch Ness monster, type thing. You picture it, and you just saw that move down the wave. I went up and down here, and the wave went that way. That's a transverse wave. See, a compressional wave is this. The pressure is like this, and the wave is moving like that. So the disturbance of the air, or whatever else is doing, is in one direction, and the wave travels in that direction. With a transverse wave, and that's why they call it a shear wave, S wave, shear, secondary, the motion is up and down, but the wave is perpendicular to that. That's a shear wave. When the motion is back and forth, and the wave travels in that same direction, that's a longitudinal wave, compression wave. This is a transverse wave, meaning opposite direction from what the wave is traveling. And these are the second fastest waves, and here's the key. They do not move through liquids. Only move through solids. Okay? Now, there is a third kind of wave, and I hate to, they just call them here up and down wave, or crest and trough wave. Most of the time they're called surface waves. And the thing I don't like about surface waves, you might confuse them with S waves. They're not. S waves are inside the Earth, just like P waves are. They're transverse shear waves. The surface waves are those, when these other waves reach the surface of the Earth, and then they create, picture this. I take a big old rock and throw it into a lake. Okay? Now, the rock is going to interact with the water in one place, right where it hits. But then you see the energy from that hit moving outward in ripple effect, right? That's what a surface wave is. The energy coming up from these seismic waves from within the Earth itself, when they reach the surface, they have nowhere to go, so they've spread out. That's why they call them surface waves. They're much like water waves. They're the slowest of the three, and they appear where either an S wave or a P wave reach the surface, and then they just spread along the surface. I don't know if you've ever seen any videos of atomic explosions where they tested, bombs or whatever. And you can see it to some extent with conventional bombs too. They have to be pretty big when you do it. But you'll see when the mushroom cloud went up, and a lot of energy like this. Then if you look at the surface, most of the time we focus on that mushroom cloud. But if you look at the surface, it just, you see waves just going in all directions, and these are surface waves. Okay, they move slowly, but they move a lot. A lot of energy is transmitted there. Okay. Now here's examples. They use the spring to represent the pressure wave, the primary wave, the longitudinal wave, the compression wave. Okay. And I can't imagine the spring staying that horizontal like this, but if you bear with that, if you take the plate on the end of the spring, push it in and pull it out, what you see is that move up and down the spring. Sometimes bounce off this and come back up. You'll see that pressure move here and then there and then there. You don't show it too well here and here. For some reason, he didn't get this one drawn well. But here, it moves down the thing. The action is horizontal, and the wave is horizontal. It moves in a horizontal direction. The wave propagation is in the same direction as the particle motion that created the wave. Okay? Whereas the shear waves, the particle motion is up and down, like me and the hose. Okay? Or as my grandmother used to say, the hose pipe. I don't know why she called it a hose pipe, but she did. Okay? And you go up and down, but the propagation is that way. Particle motion up and down, wave propagation horizontal. Okay? That's a transverse wave. Now, think about it. This wave will go through solids, that will go through solids. They're waves. The energy moves that way. But if you think about it, a liquid can be compressed and then rarefacted, compressed and rarefacted, but a liquid can't move up and down and transmit energy that way. It just doesn't happen because they've not got the crystal structure to do that. Okay, so that's why the secondary waves will not go through liquids, which turns out being important. Very important. Okay? Now, time out from the waves is sort of jumpy here, the way they've organized things. We now move to the Earth's internal structure. Then we'll come back with the waves and show us what they're telling us. So now we're in 18.2, which is the Earth's internal structure. Three main zones. Okay? We have the crust. Now we live in the crust. We work in the crust. Everything we do is in the crust of the Earth. The crust only goes down a few miles. But when's the last time you went anywhere close to a mile deep? You don't. Never. Okay. So we just about everything we do and interact with is in the crust. Okay. That's the outer shell, and believe it or not, even though we say it's a few miles deep, that's really thin. Really thin compared to the whole structure of the Earth. It's just like a skin. It's really, really thin. Then we get to the mantle. Mantle is much thicker than the crust. Okay? It's solid. And the crust itself is solid too, even though you have pools of water in it. We call that oceans. Okay? And so the pools may go several miles down, but that's just little piddling stuff compared to the whole surface of the Earth. The mantle is huge, much, much thicker. And then we finally hit the core. That's the central part. And even the core is split into outer core and inner core. So here's how that looks on a cutaway view. And they have probably exaggerated the crust here, okay? It's this brown skin that's on outside of everything. That's the crust, okay? Very thin, very even though we live there, it's very inconsequential compared to everything else. Okay. Now, they do show something else here, but we're not going to talk about it yet. We move into the mantle. The mantle is thick, way thick compared to the crust, and it's a huge portion of the earth. Totally solid rock, pretty much. I'll give you reasons for that exception later. Then you get the outer core, and this is liquid. Okay? Then you get the inner core, and that's solid again. Okay? Now you might say, how do we know this if we don't do anything but live in the crust? Well, we have these other data collection processes. Then when we put together the models and what we see, we find out it's about the only way it could be structured to produce the results we are used to seeing. All right. So, somewhere they're going to give some percentages. All right. Let's start with the crust. As I said, thin, but important, because that's where we live, that's where we work, that's where we have our beings, in the crust. But it's not very major. Oh, here we have Zachary. I know you're in here. There you are. All right. Okay. The crust covers the entire earth. Okay? We have two classifications of crust. Now, what covers most of the earth? Water. The oceans, everything covered easily 2/3, close to 3/4 of the earth's surface covered by water. Okay? Now, that water is minuscule. Those are like puddles compared to the whole earth. Because underneath the water is what we call the oceanic crust. That's what's holding the water. Now, the oceanic crust is thinner than the continental crust. Part of that is what it's made from is basaltic rock. Remember that? Basaltic rock is high iron content, therefore dark colored, high density because of a high iron content, denser materials, and most of that is formed from volcanic activity. Underneath the ocean, the crust there was from volcanic activity. The continental crust, though, is typically granite rock, and if you remember granite, very low iron content, okay? So it's a lighter rock, less dense, also lighter color, because it hasn't got as much iron in it, okay? So that's the two parts of the crust. Oceanic crust, which is basically most of the Earth's surface covered with that, but it's under the ocean. And then the continental crust, where we usually live and work and play, that's mostly granitic rock and less dense, lighter color, all that kind of stuff. Now, the crust, very thin. The next thing is the mantle. In between the crust and the mantle, that boundary, you might say there, is called the Mohorovičić discontinuity. Boy, I can't say that many times, but most of the time they shorten that and just call it the Moho. Okay, I'm a lot happier with that, the Moho. Okay, it's the boundary between the mantle and the crust. Now, this is a weird way in my mind to say it. They say the seismic wave velocity increases sharply from the crust to the mantle. I believe that from the bottom of my heart, but why in the world would they ever phrase it that way? Because most of the time your seismic waves are starting in the mantle and coming to the crust. It seems like to me they should have said the seismic wave velocity decreases sharply from the mantle to the crust, okay? Because that's what we're measuring, is that seismic wave activity, and we see the velocity decrease. increase going down, but most of the time we don't go down, we're coming back up. So anyway, it doesn't matter. Same difference. Okay? So here is sort of the pictorial indicator of that. I would say the scales are nowhere close to being correct here. Okay? Here we have a continent, and the continent is a big, thick, but light, both light colored and light density crust, the continental crust. Over here we have the body of water, the ocean. But underneath the ocean you have the oceanic crust. Now there's one thing that is something else wrong with this picture. Probably the relative dimensions are probably pretty wacko. But more importantly than that, the continental crust being denser, and that's what we show here, so it's not a very good picture. This side outweighs that side because it's more iron content in this. A little bit here, but way more here. But because this is denser, it tends to go under the continental crust. It doesn't fall up the continental crust. So this picture is a little off in that. Okay? It tends to bend downward. And you'll see that in later. But somewhere down here, underneath the oceans and the oceanic crust, or beneath the continent, is this, there's the mantle, this is the moho. The boundary between the crust and the mantle. That little wavy, uneven, irregular line there. That's the Mohorovicic discontinuity. The speed of seismic waves increases sharply if you're going down through the continental crust into a mantle, or decreases sharply if the seismic waves are coming from the mantle into the continental crust, or either crust, oceanic or continental. And that's typically, I think, the way they go, is through the mantle to the continental crust. So I would have reversed that and said it the other way. Okay, but you get the general idea. Continental crust, thicker, but less dense, lighter, you might say. Oceanic crust, darker, more iron content, and also lighter in color and lighter in density. Okay. But seldom will you see, I don't think you'll ever see continental crust, the oceanic crust crawling up. It's always dipping down compared to the continental. Okay, so that was the crust. Now we're dealing with the mantle. Now, I don't know what's going on. Yesterday, about this time in my calculus class, I just started feeling almost sick. And today it's the same thing. I'm lightheaded, my eyes are sort of blinking on me some, and I don't know. I don't know if something I'm eating or something, but it's just, I'm feeling pretty lousy, but it's not bad enough to stop. So here's the mantle. It's the thick shell. The crust is a thin little shell. Okay, but it's a thick shell between the crust and the core. Now notice this. It takes up 80% of the Earth's volume. Okay? The thin little crust, not much volume there at all. The mantle, huge amount. 4/5 of the Earth's volume is the mantle. Okay? But it only accounts for about 2/3 of the Earth's mass. Okay? Now what does that indicate to you? It takes up larger volume but smaller mass. It's not as dense. It's a lot denser than the crust, but it's not nearly as dense as the core. The core is dense, really dense. Now, the Earth's mantle, remember we mentioned this before, composed largely, mainly of olivine, which is a ferromagnesium silicate. It is a silicate, but high iron magnesium content. Dark color, really dark color, is the mineral olivine. It was the one, if you recall, in the Bowen series of things that come out of solution, one of the first to come out at the very hottest temperatures. It comes out of solution. Okay, high iron content. Okay, so that's the mantle. Now, how do we know this? Well, 3 data sources. We have not drilled into the mantle to see. Okay, we can't. We don't have drill bits long enough. We don't have drill bits strong enough. There's no way we could drill. If we ever got to the mantle, which I think the Russians have a time or two, they can't go very far. Okay, pretty major difference there. Okay, 3 data sources. The seismological data. Okay, you've said this before. You're saying it now. What do we mean by this? Hang on to those questions. We'll get to them shortly. Okay? But that makes a lot more sense than the nature of meteorites. What? What do meteorites have to do with the mantle? Well, except for the fact everything in the solar system came from the explosion of the sun, right? So therefore, meteorites should reflect things that we see in the earth. And if we see things in a meteorite that we don't see on the surface, there's a really good chance that could be something subsurface, as in the mantle. And we do see things in meteorites that are nowhere close to what we see on the surface of the earth. So that's the indicator. Probably that's what our interior looks like. And this, to me, is the one that's the most logical. Materials ejected by volcanoes. It just depends on how far down that magma came, but this would be a good representation of what's in the mantle. Okay? Now, here's another thing, and they just sort of pull it out of the air. Basalt correlation. And they really don't do a good job of describing or explaining what they mean by this. But it goes back to the meteorites, you see. The basalts, which are mostly in the oceanic crust, remember? And by the way, I meant to say this earlier. Even though we say the basalts are in the oceanic crust, when my wife and I, she had professional meetings a couple of summers ago, it's during the week we had off, either between spring and summer, or between summer and fall. So I got to go with her. It was to Park City, Utah, is where our meetings were. That's near Salt Lake City. But because I had the week and she had the week to do, we just took a little mini vacation while we were out there before our meetings, before and after our meetings, kind of. And there were areas that were called basalts. And this is up in the high plains. I mean, almost in the mountains. Here were just layers of basalts. Well, what does that mean? That was at one time underneath the surface. It was underneath the sea. And things have lifted that up. Well, think about this. How do you think the Great Salt Lake got there? You know, Salt Lake City in Utah, the Great Salt Lake, is the remnants of if it wasn't an ocean, it was a bay or something associated with ocean. It was salty, okay? But somehow it got lifted up. And that's how the basalts got lifted too. So, the basalt correlation. Close to the silicate chemical composition of the stony meteorite. So there's one way the nature of meteorites correlate to what we see. The basalts are close to the silicate composition of the stony meteorite. So that's one way the nature of meteorites. Now, the most common volcanic rock coming out of a volcano are basalts, okay? Because coming out of a volcano means they reach the surface and they cool quickly. And remember, basalts are very fine-grained, high iron content. And on the surface, on the crust of the ocean, the oceanic crust, volcanic activity cooling real quickly when it hits that cold water. So that's where that comes from. So the salt correlation ties in with the nature of meteorites and with the volcanic similarities, I'll put it that way. Okay. Everybody finished with the mantle? So let's really go deep to the core. Okay. Now, I kind of expect you to remember a little bit about our percentages. What percentage was of the Earth's volume was the mantle? 80%. This tells us the core is 15% of the volume of the Earth. That would leave the crust to be what? 5%. Even though it covers the entire Earth, it has to be awfully thin that it only accounts for 5% of the volume. Okay, how about Earth's mass? What did the mantle consist of? 2/3, and the core 1/3. Guess what? The crust is so tiny a percentage of the mass it doesn't even register. Okay, the vast majority of the mass is mantle, 2/3, core, 1/3. The Earth's crust is almost in the noise. Okay, it doesn't even pick up. All right, now we're getting closer to how the seismological data correlates, how we use that in defining or estimating or predicting what the structure of the Earth is like. Okay? Now, this is a pretty interesting illustration. These are your P waves, primary waves, pressure waves. Let's say there was an earthquake somewhere up here. Now, doubt if it was in the crust. It could have been, but more likely it was somewhere down in the upper part of the mantle. Okay? Let's just say that. Assuming it. P waves go out in every direction from it. Okay? This is a cutaway in every direction from that. And these P waves, because as you go down, you go into denser material and they sort of get bent upward. So that's why they represent them this way. Okay? Primary waves, P waves, compression waves. Well, looky here. Something happens down here that brings them closer together. They're getting diverging up here, something converges here. Okay? And then begins to diverge again, and they come out over here. There has to be something different in there to make them do this. Now, how do we know they do this? Because you have this, what they call a shadow zone here. If you were, and they do have, remember they have these seismographs all over the surface of the Earth, on every continent, probably some that are attached to the ocean somehow, but everywhere they got these seismographs. And when there's an earthquake here, you will see it, feel it, those pressure waves, primary waves. From there, 103 degrees. That's 90 degrees is a quarter of the way, so this is over a quarter way around the Earth. You will sense the seismographs will pick up these in all directions, 103 degrees away, and then they go quiet. Absolutely none of your seismographs here will pick up the thing. Here they're going crazy, and here they don't pick up the thing. And then down here between 142 degrees, they go crazy again. Okay? What does that mean? Somewhere in here, and we can estimate the radius of this, and this is probably way exaggerated here, just for purposes of this. It had to have been doing some contraction here and then spread out again in order to make those waves. Well, there has to be a pretty major discontinuity there. What would account for that? Solid to liquid to solid. That would account for that contraction and spreading again. Okay? And the fact that it contracts to in here and then spreads out past there, that would indicate this is probably another boundary in here, solid, liquid to solid to liquid. Sure enough, that indicates We can't go down there and check, but it indicates. You do modeling with different things, try to control different features of it, try different things. Best model to predict this kind of activity is coming from this, that this fits it really well. Because the waves do come all the way through here, P waves. Nothing in here between 103 and 142 degrees. Okay? So, the P waves are refracted by the core, producing, refracted means producing the P wave shadow zone. No direct P waves are seen between 103 and 142 of arc from the earthquake, and they're used to calculate the shape and size of the core, and in some senses the composition of the core. The source of the data on the interior make up the core. This is the major source. Okay. Well, couldn't that just be another discontinuity like the Earth's crust to the mantle? That's a big discontinuity. The speed changes, but that's solid to solid. Couldn't that be done by this too? Maybe. Yeah, perhaps. I think so. Okay? Except for this. The S-wave seismic data show a much larger S-wave shadow zone. In fact, the 103, now notice here, I don't know if you can pick up on this where you're sitting. The pressure waves go in the same direction as the propagation, so they're just drawn as lines. But the secondary waves, remember, those are transverse waves, so they're drawn as squiggles, okay? Because they're moving this way but propagating this way. Okay, so that's what they're here. The 103, the S waves come, they're a little bit slower than the primary waves, we'll get to that later, but they make it to 103 degrees on any side, all the way around from the earthquake. No problem. But rather than have a 103 to 142 shadow zone, this whole thing's a shadow zone. The entire thing. No S waves make it through. Now, what was another characteristic of transverse waves? They don't travel through liquid. That nails it at the core, and they can almost define exactly the diameter, radius, you might say, of that core, how much of that must be liquid. Because to produce this pattern, that has to be a huge block in there. Okay? And then the primary waves, the fact that some come through, they can go through liquids, but that also indicates that contraction in the middle, which probably means you have a solid inner core. Okay? Wow, who would have thunk it that the waves from earthquakes tell us about the structure of the earth? Pretty incredible. And pretty irrefutable too, because these transverse waves cannot go through liquid, so the core, somewhere in there has to be a liquid core. And then the pattern that do make it through of the primary waves, that indicates there must be a contraction in there to meaning it goes back to being a solid again. Okay? Is this known for sure? Not probably absolutely certain, but it certainly is indicated. Okay? The S-waves seismic data, big old shadow zone. Anything past 103 on the other side, that's just a little bit past a quarter of the way. No additional S-waves ever make it through. Okay? So the core acts like a liquid, not allowing S-wave propagation. Core has then two parts: liquid outer core, which you see from the S-wave shadow zone, and the solid inner core, which can only be modeled by that coming in and going, spreading back out again, supported by the S-wave and P-wave data. And other things like gravitational effects and other things too, all are supported, and by this kind of a model, it supports everything really, really well. So all the pieces put together indicate a pretty safe bet this is how it is. Pretty clever they were, the people to study this, model it, test it, try different things, and come up with a really good indication of what our internal structure is, even though we're never going to know that. And by the way, Journey to the Center of the Earth, anyone ever remember there was an ancient movie that way? Okay. Fiction, fiction, fiction. Never happens, never could happen. Even if it could, they'd be burnt to a crisp, and then you'd let all that high pressure molten rock come spewing to the surface. We don't want it to happen, okay? It's fiction, total fiction. Not very much science in the fiction either, mostly fiction, okay. All right, ready to move on? Other core evidence. And here we go back to our meteorites again. Okay? The iron meteorites are mostly iron and iron nickel alloy. And guess what we think the center of the Earth is? Iron and iron nickel alloys. Exactly right. Thought to mimic the chemical composition of the core. Where else would they come from? Nothing else in the solar system is mostly iron and iron nickel. You know, very few silicates. It must be what? Our core. Those are little chunks of core that got spewed out there. Next, the Earth's magnetic field. The source is that turbulent flow within the liquid core. Where else could you have moving charges in there? Why would you have moving charges except you have a lot of, I'll picture this. Now, let's go back to their picture. All those little surfaces look like perfect little spheres there inside little spheres and stuff like that. That's not how it is. Nowhere close. The mantle is probably, that inner part of the mantle is really rough and jagged and different types of rock, and then the core, the outer core, which is liquid, probably is somewhat, phasing from being liquid to solid. There's probably a lot of friction and interruptions and stuff, and that's what creates this turbulent activity, turbulent flow within that liquid core. And that's why electrons get knocked off and moved around, and that's what creates charge, the flow of charge. The material must conduct electricity, so guess what the odds are that material is? Iron. Probably not copper, probably not silver, more than likely iron, because it's also naturally magnetic, and that would be iron, nickel, or cobalt. There's not that much cobalt down there. Okay? So the meteorite and the magnetic field data are consistent with an iron core. Okay? That would explain why we have these big chunks of iron and iron nickel alloy flying around out there, and the fact that we have a magnetic core. It must be iron. Okay? Almost would have to be. Iron and iron nickel alloy. And I think I've said it before, let me say it again. The only three naturally occurring magnetic elements are iron, nickel, and cobalt. And there's just not that much cobalt out there. Plenty of iron and nickel, so that's why we think that's our inner core. Well, both of our cores. The inner core and the outer core. So no one's ever taken samples of any of these. No one's ever been there to see. But all this different, diverse, data collected from so many different sources, and all seems to lead to the same model, or be defined or described or adequately parameterized, you might say, by the same model. That lends a lot of credence. If there's just one data source, that could be distorted, it could be have faults in it, but when you have all these different independently gathered pieces of information that all tend to suggest the same model, you feel really good about that. You know, that we probably do have, it may not be totally correct, but it's predominantly correct. Okay. Got it? All right. Now, we're going to look at a little more detailed structure, because nothing we've done or said indicates anything about why plate should be, the surface of the earth should be these big old floating plates. Okay? Well, here's that detailed structure. I told you we were going to get to it a little bit. Here it is. Remember what a sphere is? A ball. Okay? So we have these different spheres. Okay? The earth itself is a spheroid, you know, stuff like this. Well, here we have a ball within a ball, and this is called the asthenosphere. It's a thin, hot, elastic, semi-liquid layer somewhere in the upper mantle. Okay? Now, let's go back and review what we had said before. We have the crust, oceanic crust underneath the water, continental crust, much thicker, but lighter colored, lighter density is the continental crust, mostly granite. The oceanic crust, mostly basalt underneath the ocean, but thin, but very dense. Then you hit the moho. The moho-rovichic discontinuity is the boundary between the mantle and the crust in the upper part of the mantle. Then you go down into the mantle. Now, we don't know how far, but it's probably not super far in there. And then you hit this thing called the asthenosphere. Now, what do these things mean? It's a thin layer, a thin sphere, shell you might say, very hot, elastic, meaning it rebounds and goes back to its original shape, but it's a semi-liquid. You know, mostly, you know, remember the mantle we said was pretty much solid, you know, olivine, you know, solid iron rock, you know. But this is semi-liquid layer somewhere in the upper mantle. Okay? Now, if we didn't have enough spheres, remember what litho was? Rock. The lithosphere. The solid layer above the asthenosphere that includes the upper part of the mantle and the crust. Includes the entire crust, the moho-rovichic discontinuity, and the upper part of the mantle. So all that is in what we call the lithosphere. Now, this lithosphere is made up of these rigid plates, and they literally are like they're floating in the upper mantle on that asthenosphere. That's where plate tectonics come from. The inner part of the mantle is pretty much fixed. It's pretty much rigid, we think. It's above that asthenosphere, which is this thin, elastic, hot, semi-liquid layer in the upper mantle that's in there. That forms the boundary between the lower mantle, which is solid, and the upper mantle, which is in pieces, chunks, plates. Tectonic, no, that's okay. And so that's the more detailed structure. That asthenosphere is the thing that the plates float on. And that's why they can move, because they're on that semi-liquid elastic layer somewhere there in the upper mantle. Okay? And all the rock above the asthenosphere, including the crust, the upper mantle and the crust, and it includes the boundary between the mantle and the crust, which is Mother Earth, which is discontinuity, includes that. That's your lithosphere. Okay. Rigid plates that float around, in the upper mantle. Goodness gracious, I'm totally running out of gas. Okay. I haven't been turning the pages as I should. Now, there is an interesting little blurb. All right. I knew it was in here, and we'll come back to this later. Y'all remind me. When we do, it is the last of this chapter too. Okay. There's a little table here, comparison of the oceanic crust to the continental crust. I should have mentioned this way back there. The oceanic crust, we think, is less than 200 million years old, which to me indicates just about totally made from seismic activity. Very recent seismic activity. The continental crust, up to 3.8 billion years old. That means that was what was formed when that molten surface cooled. Okay, that's the continental crust. But the oceanic crust, much newer and much thinner. Thickness of the continental crust, 3 to 5 miles. Oceanic crust, 3 to 5 miles. Thickness of the continental crust, 6 to 47 miles. No, we've never been that deep in anything. But here's the deal. The basaltic oceanic crust, the density around 3.0 grams per cubic centimeter, and the continental crust, which is mostly of granite and some other materials like that, 2.7 grams per cubic centimeter. So not a huge difference, but some difference in density, mostly because of the iron content. Okay. Now, they love to throw these little problems in. Sometimes they're useful, sometimes not. What is the height at which the oceanic crust floats on the mantle? And this is assuming Again, this is just sort of a made-up problem, so I wouldn't waste a lot of time with it. It's sort of interesting, some things I'm reading in it, but it sort of is beyond the scope of what this book is doing, so I'm just going to skip that. Okay, I think we got mostly done. Now, before we get into the theory of plate tectonics, 18.3, there is a lavender blurb at the top of that page, 464, on seismic tomography. What in the world do we mean by that? Sounds like a made-up term, and it probably is. Has anyone ever heard of a CAT scan? Sure. Does that have anything to do with felines?
No way.
No way, okay.
I'm sorry. I think CAT scan is still when a woman gets pregnant, they have to go through the process of a CAT scan to see the.
Yeah, that sounds. I don't know if CAT scans could be harmful to the fetus. I think they probably would tend to. They may not be, but the ultrasounds are what they use for that.
I'm sorry, I just got confused.
Yeah, that's all right. It's but what okay. Here's what I think that stands for. Computer assisted tomography. That's what a CAT scan is. They also have PET scans. I hadn't heard of that one and that has nothing to do with felines or canines, by the way. Okay, those are my older brother had a little spot or cyst or something, nodule or something on a lung, and so they're going to do a PET scan to see if any other organs were affected, and that's something that can. So I don't know what, but I guarantee you what the T stands for. More than likely, tomography. Okay, and what this means is you're looking at the structure of things by taking another measure, a computer-assisted measurement of the waves coming out of something. And so seismic tomography basically draws slices of whatever you're wanting to study, the center of the Earth. And this is sort of explaining how we use the seismic waves and other things to come up with these models. So it's a good, I almost want to say fun read. It may not be all that much fun to you, but it's an interesting read, I think. So you might want to take a look at it. All right. I think we're ready for a theory of plate tectonics, and y'all have been writing away, so you probably already have this done. So earlier we called it continental drift. Okay, there it is. I knew it was somewhere in here. The individual continents shift positions on the Earth's surface, but incredibly slowly. Okay, you can't, well, I don't want to say you can't measure, you can't tell much difference in a lifetime. Okay, though they have been able, with things like lasers and things like this, to actually measure that, yeah, it seems like maybe we're half a centimeter further away than we were 10 years ago. You know, half a centimeter in 10 years. That's not a big, over thousands of miles. It's not much, but they have been able to determine. They do shift positions, but incredibly slowly. The patterns between the continental shapes can be fit together. And I think that's what they're going to show here. And I think they showed this. Trying to remember if I've seen a better picture. This may be the best one they got. Notice how the hump in South America, this is basically Brazil, how that fits almost perfectly into the armpit of Africa, okay? And sure enough, it really does. Now, there's been a little bit of twisting and moving, but still has. Notice also here how North America angles up this way, but Europe angles up the opposite way. And that looks like that could fit, okay? Now, the dimensions aren't quite right, but this bulge in Africa here, I mean, that comes pretty close to filling the Caribbean Sea, the Gulf of Mexico, and this area right in here. Looks like it's a little too big, but yeah, things could have shifted some. And so there's lots of things that look like, yeah, it looks like these have drifted apart and maybe swiveled a little too over time. Over much, 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 much time. Long, long periods of time. Now, another thing that they don't really focus on too much, look at this. There's a wedge of water that goes up. And actually, does anyone know what's at the top here? Second? Suez Canal. The only remaining land link between Africa and Europe, and Asia. And they did a canal so ships could go through there. But look at this. That is basically an area that's drifting apart. Okay? And here's another one. Well, guess what? Here's a plate in here. This is the Arabian plate. That's almost defines the Arabian plate here. African plate, Eurasian plate, Arabian plate. So yeah, a lot of things are really amazingly related, you know, to the concept of the continents drifting apart very slowly. Okay? Here's the current belief, or at least one theory of it. All the land masses were part of a single large landmass called Pangaea. Now, if you want the actual root here, this, the word we get for geology, geography, this is Earth, the Earth's surface. Gea, Pangea, all one. Pandemic is an epidemic that spread over huge areas, not just an epidemic could be in a small cluster or something that everybody around there is getting it, but a pandemic is when the whole world is getting it. So that's what pan means, over all the earth. That's what it means, over all the earth. Pangea. One big supercontinent. Okay? And the early ideas were continental drift. They didn't know about the plates and things like this. They just thought somehow the continents had drifted further apart. And that was all based on the fact that South America fits into Africa, Africa fits into the Caribbean and Gulf of Mexico, the North America slants like this, and Europe slants in the opposite direction. It just all seems to fit way, way too nicely. And I can't remember the name of the guy who first proposed this. And it's probably somewhat intentional that he's forgotten because he was laughed out of the room. When he first proposed this to whatever group, Royal Society, or whatever, people said, "Are you nuts? Get out of here. This isn't worth our time." That there could be, the continents aren't moving. They're fixed. Can't you tell that? They're just sitting there. You know, they haven't moved. So his notion was thrown out completely. And it was probably I don't know. I'd say centuries. I don't know for sure. I was wanting to say decades. I think it was more like centuries passed before. Then they look back. I mean, whoever it was had been dead for generations. And then they looked back and said, you know, he was right. Whereas he was ridiculed during his lifetime. Absolutely nobody believed him. And over time, more and more people said, you know, he must be right. That looks like he's right. And now, if we knew who he was, I'm sure someone must know. He's a hero. Of course, it did him no good. He's been dead for, like I said, probably close to centuries. All right. Now, we're still doing, okay, we're doing theory of plate tectonics. Now we're looking at evidence for plate tectonics from these various places. First place is going to be the Earth's magnetic field. Okay. Oh, man. Stiff and sore. This is indicating that plates are moving. Igneous rocks, what kind are those? Igneous rocks? Second? They came from molten, magma, or lava, if it's on the surface. The igneous rocks record the Earth's magnetic field strength and direction. This is almost unbelievable. This almost sounds like science fiction, but it's true. Okay? There are two types of iron ore that settles out when there's magma extrusions. There is some that's called hematite that is just iron ore. Okay? No inherent magnetic characteristics at all. You can make them into magnets, but naturally they're not. And then there's magnetite, whose chemical composition is identical to hematite, but this happens to be magnetized. Okay? Naturally occurring magnets. Okay? Now, I'm going to kind of tie this into what I understand, and it may only be my theory, but it's what I understand from what I'm reading. Notice here it says, igneous rock record Earth's magnetic field strength and direction. I don't know if this is right or not, but it's the only way I can understand it. Right now, the Earth is a magnet. You can hold up any compass, and it's going to point to the north. Okay? And what we're going to read in just a little bit on the bottom part of this slide, you're going to see that it's changed direction many times. Okay? What? How could it change direction? Unless, the Earth's spinning and the charges have to be floating around somewhere in there in the core to the magma boundary, mantle boundary, somewhere in there. That's probably where the charges are spinning. And evidently those charges are not spinning quite the same way as the Earth. They must be going through a little bit of a very slow change, and sometime then they actually reverse themselves. And then they change again and reverse themselves. Because not only do you have direction changing, you have the field strength changing. And that would be accounted for if they followed a pattern. Like just about everything in science follows this pattern, a sinusoidal curve, where something might be zero, very strong positive, stronger positive, then start decreasing positive, goes to zero again, then goes negative, but very weak negative, stronger negative, stronger, and it gets strong again, weaker, zero, stronger, weaker, zero, stronger, negative, or positive, negative, alternating. Everything else follows a pattern like that. We call it harmonic motion, simple harmonic motion. Maybe the movement of those charges inside the core of the Earth, the liquid core, may be doing its own sort of dance in there that sometimes is strong, sometimes is weak, sometimes changes direction. Okay? So, we know that's the case. The igneous rocks record this. Okay? And what happens is, when there's a volcanic eruption, you got this liquid stuff. The Earth's magnetic field, right now, let me give you this. This really happened to me. So I know it can happen and does happen. We were, when we first bought the house where we are now, there was a really rickety shed at the back of the garage. Really rickety shed. The floor was pretty much rotted out. It was on a fairly steep hill. Nothing really fit squarely anymore. The wood was rotting. Termites had been in it. That's, I think, where they stored their lawnmower and things like that. And it was in really bad shape. It leaked, and it was actually felt dangerous to even go in. It was just that. Well, so that was part of it. It attached to the garage. It was part of the upper part of it is where the privacy fence picked up and went up to the edge, up to the back of the property. Well, if we take down the shed, which we had to, then the privacy fence has a big gap in it. And it was sort of a mess. And then when they did the survey, we noticed the surveying stakes and lines were outside that. So in other words, our neighbor had been mowing part of our yard, the backside of our garage and the shed and the property, the privacy fence. That was about 4 feet inside our property line. So the neighbor had 4 feet of our yard over there. And they were mowing it, keeping it nice and stuff. And then we had this ugly old shed here. And the privacy fence wasn't in good shape either. So we were deciding what to do, and we talked with the neighbor, and she was renting. She talked with the owner in Tuscaloosa, and they said, oh yeah, we know that's their yard, not ours, but that's how it is. We've had it like that for years. Well, we need to replace the privacy fence. Do you want us to put it back on the property line? Sure, yeah, absolutely, whatever. So I was putting in a new property, and we took out the shed too. So I was putting in a new privacy fence. Okay, so what I had to do was, and the sections of the boards that you use are 8 feet long. So I had to have a post every 8 feet, from the corner of the lot down to the near where the garage was. And it was a new thing. And our lot lines up almost perfectly north-south. That fence was almost perfect north-south. So what I was doing, I put in the post at the top, right near the iron stake that showed the property line, and one down here. And then I was going to put in the other posts 8 feet apart, but I needed them straight. So I took a string and tied it to the top post, and it went downhill, so it was sort of tough to do. Near the bottom of that top post, and by this time it was near the top of the end post down here. So I was hammering the nail, a metal nail, an iron nail, into the top of the post, because I had to get it off the ground, the hammering in it. I'm not a very good hammerer. My dad said they were all right-handed hammers, and I was left-handed, and that's why that was his theory. So anyway, the nail went flying, and I thought, oh my goodness! I just happened to be letting the hammer hang down from my hand as I was looking, scratching around in the leaves and grass, and suddenly the nail attached itself to the hammer. What? And then I realized I was hammering, drawing that nail almost in the direct north-south direction, in the direction of the Earth's magnetic field lines. And anytime you jar or perturb or something like that, a magnetic material in the presence of a field, they call them their domains, line up according to that. That's how, when you take a magnetic material that's not magnetized, a piece of iron, and stroke it against the side of a magnet, you can make it a magnet. Okay, a needle, a pin, that's iron material. I don't know if you've ever done it. You can do it anytime you want to. Stroke it against a magnet, and it becomes a magnet because you're perturbing, you're shaking up those domains, and then they line up according to the magnetic field. Well, that's exactly what the magma did. When it would erupt and there was a strong Earth's magnetic field line, they would line up in that and point in that direction, actually like this, okay? But then when there was a weaker field, there'd be hardly any magnetization at all. But then later there'd be more, stronger. So they knew that the igneous rocks recorded the magnetic field strength because it'd be more lined up here than later on fewer, and then later on more again, and fewer and more. So you could see the field strength was increasing and decreasing. Okay? But here is the crazy part. The Earth's magnetic field varies in strength, we understand that, but also direction over time. There have been 22 reversals over the past 4.5 million years. They have taken cores down in the Earth's crust, where the magnetic material is labeled, taken them down, and they are able, through fossils and other things, carbon dating and things like that, to estimate the age of these things. And over the past 4.5 million years, 22 times the field lines have changed direction for the Earth. North is pointed this way, the north pointed that way, the north pointed this way, the north pointed. 22 reversals. And in between, there were times where there was hardly any field at all. Okay? So, that's how we know these have happened. Okay, so what does that have to do with plate tectonics? Well, here's what it has to do with it. Well, here's the picture of it. When the cooling lava, the magnetite crystals aligned up with the direction of the Earth's magnetic field, it was pointing this way. Okay? And you can see that, and see it through several eruptions. But then all of a sudden, you have some pointing this way. And then you have more pointing that way again. 22 reversals as you keep going lower and lower, deeper into the layers of volcanic activity over 4.5 million years. What? Okay. Now, what does that have to do with plate tectonics? Interesting for sure, but why would that have anything to do with plate tectonics? Okay? going to be a little bit of a timeout before we see this, before we get the answer to that question. Evidence from the ocean. Okay? See, they started giving us evidence from there, but they didn't finish. Here's evidence from the ocean. In the middle of some areas, there are these oceanic ridges. Okay? Okay, these coincide with a lot of submarine, meaning under the surface of the ocean, earthquakes. There is a rift along the crest of these. Large amounts of heat escapes from the crest, and one of the primary examples of this is the Mid-Atlantic Ridge. Okay? And when they say Mid-Atlantic, it's really Mid-Atlantic. It starts up here, and goes down here, almost directly, same distance from either continent here, goes in between here, goes down like that. Middle of the Atlantic, though the Atlantic is wavy, it's wavy. Okay?
Isn't that like where the two oceans don't mix?
The what?
Two oceans don't mix?
No, not quite. I think what you may be thinking, the Amazon River, there's a dark Amazon and the light Amazon, and they come together and they float next to each other when they're one river, and they don't change colors, for miles and miles and miles. Okay, and another thing that may be what you're thinking of, in the Azore Islands, somewhere up there, there's two lakes that are separated by the narrowest finger of land. They're two completely different colors, So yeah, you have some of those things happening. No, the ocean mixes here, but they've been able to detect high temperature right along this ridge. Why is that? Because there's magma coming up and becoming lava right there in the middle. And an earlier edition of this book sent with it a packet of audiovisual materials. And I could play that on my computer and show it. It won't work anymore, I don't know why. And you could see bubbling in the bottom of the ocean. They had a camera way down there. You could just see this magma rolling out. And you could just follow it. You could see it happening as you went. It was a plate boundary, okay? Literally a plate boundary. Now, the magma comes out and makes these crests, okay? The heat comes out, you can measure the heat. That's what makes this Mid-Atlantic Ridge, okay? Now, we also have oceanic trenches. Now, I see a little less reason for bringing these up now, but it indeed is true. These are long, narrow, but very deep troughs with really steep sides. They always run parallel to the continental edges, especially on our west coast and South America's west coast. I mean, when I was in the Navy, we'd leave San Francisco and go out to sea, and they were taking soundings and things like this. I mean, you get just a little way out, and boom, the bottom goes way, way down. You go out a little further, and it comes back up again. That's this oceanic trench, and it's all along the western boundary of North and South America. I believe it's all around the western boundary here, and there are other places where it happens. Eastern, not so much, but western, definitely, okay? Now, long, narrow, deep troughs, steep sides, always running parallel to the continental edges, especially where there's different continents. Remember, the continental plate here, this is still North American plate. This is Pacific plate, okay? So, different plate. This is a gradual shelf that goes out here. I think probably the same thing here. Over here, not so, okay? Now, again, they just tell you just enough to get you almost there, but nothing's proven anything yet. Hardly. It's just sort of suggested. So here is what we call the seafloor spreading hypothesis. Hot molten rock moves up from the Earth's interior, emerging along these rifts, bubbling out of there, and I've seen pictures of it, motion pictures of it. The outflow is in both directions, and it creates new rocks. And it's always doing this. It's been doing it. Now, go back to our drills, those cores that they've made. It showed 22 reversals. The drilling evidence showed thin sediment layers near the ridge becoming thicker and thicker and thicker and thicker the further you get away from the ridge toward the continents. Okay? Now, other fossils and rocks near the continents become younger near the ridge. So you get old deposits here and much younger deposits here. You won't see any of the old fossils that you see here. It's not old enough. That's all new stuff right there, brand new stuff. Okay? So there's the seafloor spreading hypothesis. This, by the way, is on page 466. It's not a subtitle, but it's a thing. Now, a couple of their slides here I don't find really all that great, but they're indicated. So let's look at what they found. These areas here near the continents, from 65 to 135 million years old. The fossils, the carbon dating, everything they have indicate these are ancient. But inside them, there's a band that's only 53 to 65 million years. Then there's a band that's 38 to 53 million. Then another one 23 to 38, 5 to 23 million, and this in the middle, this one right here, is only about less than 5 million years old. Nothing in there is more than 5 million years old. None of the carbon dating, none of the fossils, none of anything. So you get the most recent stuff here, older stuff here, much older here, and very ancient out here, which means it indicates this is all new. And the older stuff gets further and further away, which means at one time, these were together. The yellow was probably together because it's same age on this side as that side, okay? And how could that be, except this is all new material in between? The continents have been spread, okay? All right. Okay with that? Oh, still writing? Okay. I'll sit for a minute. I was feeling better than I did earlier, but man, there was a spot there that I was feeling really rotten. So again, lots of different evidence from lots of different places sort of coming together, all pointing toward the same direction. The shapes of the continents, yeah, that could have been just happenstance. But the ridge in the middle of the ocean, where did that come from? The fact that volcanic activity is right along that ridge. And by the way, I hope this won't bother you too much. Let me go back here to this picture here. Look at who's right up here. Iceland's right on. Iceland is a place where that continental ridge, the boiling lava came all the way to the surface. It's a volcanic island, and maybe a couple of them there. And the whole island is a volcanic island, and it's right in the middle of that ridge. So it was formed by that. The whole country, the whole island was. Did y'all finish? I know I turned back. Okay, still working. So part of that rift, part of that ridge actually came above the surface and became Iceland. And Iceland still erupts fairly regularly. Not like Kilauea does or something like that, but it wasn't more than 10 or 15 years ago it had such a major eruption in Iceland that they had to shut the airport in Britain down because there was enough ash from the eruption from Iceland that they didn't want to fly planes and suck that into their expensive engines and damage their engines. They had to shut it down and not have jet flight anywhere close to that until the levels of particulates came out of reduced out of the air. Pretty amazing. Okay. Got it? Okay. Now let's get back to the magnetic layers there where they shifted directions. The paleomagnetic, paleo pretty much means old magnetic patterns of the magnetic strips in the ocean floor basaltic rocks that we were talking about before. Identical magnetic reversal patterns on both sides of the ridge, but older and older the further you get away. So those patterns we saw, you see it in the yellow, you saw it in the yellow there. You didn't see it in between. Then you had other patterns. It's just amazing. Identical magnetic reversal patterns on both sides of the ridge, only you get fewer of them in the middle, more of them on the edges. The patterns match those found elsewhere, providing age determination. Hey, they got it nailed pretty well. Not exact, but really, really well. My memory's right. This is the slide I don't really care for too much. It's all right, but it could be have been done a lot better. To me, rather than doing vertical layers here, it would have made a lot more sense to put them sort of horizontal layers, because that's really what's happening. It comes up and boils over. They don't form. There is a little bit of that because it is moving further and further apart. So there's a little bit of vertical layering here, but it's far more, it would be a mixture of vertical and horizontal. But you get the general idea, the plates are moving apart and you got new material on either side. But they would be in horizontal layers too. So this would have many more reversals. This would have fewer reversals here, hardly any reversals here. Okay. Maybe one or two in 5 million years. Okay. So I don't like the vertical, what looks like vertical layers, which almost doesn't make sense. I mean, it makes a little sense, but not as well as it could have or should have. Because we know those layers are basically horizontal layers. This would have to be vertical layers, and that wouldn't really tell us a lot. But the magma comes up and spreads like that, rather than just being spreading like that. Like I said, other things like carbon dating. Do y'all know what I mean by carbon dating? Is that like Match.com? No, it's not that kind. What do we mean by carbon dating?
What's the word?
Huh? Carbon dating. That's not one molecule of carbon going out with another one. That's not what we mean. Okay. What it is most of carbon in our atmosphere, and there's lots of it out here, is carbon 12. That's the stable carbon isotope. It's there, ubiquitous everywhere. But there's a slight amount of radioactive carbon called carbon 14. Okay? And the older it is, and all plants and animals and fossils and everything else have carbon in them because carbon's in every living thing's molecule structure has carbon in it. And the older a fossil is, the less carbon 14 it'll have because carbon 14 decays away and it takes like, 1,400 years for half-life. So it's a very slow decay, but over time you can measure. So what they do, they find the fossil, they measure how much carbon-14 is in it. If it has a lot, that's a recent thing. It's not really much of a fossil. If it has very little, it's an ancient fossil, because the assumption is that the carbon-14 percentage in our atmosphere has not changed much over time. They think it all happens up in the ionosphere, where the radioactive material from the sun, the high energy gamma rays, knock carbon around and make some of them unstable. Okay, so they think the carbon-14 in our atmosphere is fairly stable over time, but it decays away inside the fossils. So therefore, they can approximately date how old the fossils are. So that's what I meant by carbon dating. Okay, just to explain that. Okay, let's go back to our lithosphere, which is the rock layer of the crust and the upper part of the mantle. That's the lithosphere. Okay, that's what's broken into these plates that float on the asthenosphere, which is that hot, elastic, semi-liquid layer. So this is the basis of plate tectonics theory as we currently understand it. The lithosphere is broken into fairly rigid plates. Not totally rigid, but fairly rigid plates. The plates move on the asthenosphere. They float on it, you might say. They slide on it. They move around on it. The earthquakes, volcanoes, and other rapid changes in the Earth's crust occur most often at the plate edges. Not always, not totally, but at the plate edges. There are 3 plate motions. We're going to talk about these in gory detail. Probably not today, because we only have about 5 minutes left, but let me at least introduce you. Divergent plate motions, that means they're moving further apart, like the mid-Atlantic ridge. Convergent, meaning they're crashing together. Okay, we'll talk about some notable places where that's occurring. And then we have also transform plate motions. That means trans meaning kind of against, okay? So they're sliding past each other, except sliding is not a good word. Moving past each other, and that's a transform. So they could be either diverging, moving apart, converging, crashing together, or transform, which means they're basically moving past each other. Okay, and all of those motions produce either earthquakes, volcanoes, or other major seismic events. Get up the picture here, and this again is that the plates we were talking about. A little bit bigger picture there. Now this makes it look like the Antarctic plate is huge, but what they've done is taken a sphere and put it on a flat sheet of paper, and that makes Antarctic, which really is pretty small down there, look huge because it got spread out over the whole length, and the length is not the same. Probably the same is happening up there, but they don't show as much of that up top. Okay, and we went through this before, so I'm not going to do too much on it again, but notice the Arabian plate is bounded on the north side by, okay, this is the Red Sea area down here. That's the Persian, I think it's the Persian Gulf up here. So this plate is basically bounded by 2 fingers of water where the plates are separated, okay? And just for a little bit of emphasis here, if you follow the San Andreas fault down far enough, there is a finger of a peninsula called the goodness gracious, it just flew the coop. Baja Peninsula. It's just south of California in Mexico, and it's a long finger that goes down there, and the San Andreas Fault, as far as I can tell, goes right in there. That's what made that finger, and the water is the fault line in between. I don't know that that's absolutely true, but it sure looks like it to me. Okay? And I hope that I'm not misstating this. Right in here, somewhere in there is Israel and Jordan and all that. It's right in this mix here. And I'm almost certain that the Dead Sea, the lowest part of the lowest landmass below sea level, way below sea level, is right somehow connected with that boundary there, where things are happening. And there's a part of Africa in here that the same kind of stuff is happening. Literally, the spread is occurring and land is subsiding. Okay, it's very slow, but it's happening. Okay, I think that's going to be all we have time for today. So we'll pick up next time, I think, with the one that's divergent boundaries. So if y'all want to take a quick break, 5 minutes or less, let me just, I'll come right back to it. Let me just, yeah, we're going to start next time with divergent boundaries. I'm sorry? $1? I don't bring my wallet up here to class. Sorry. I probably do down in my office, but I don't up here. Yeah, we're going to have about a 5-minute break. And when you, I should have said, when you come back, I'll probably have on the board what room to go to. Okay. I may still be in here myself. But. Did you finish with this? You did? Okay. All right, I'm just going to change screens, and then I'm going to put... Okay, what I'm going to do here is I'll type on here, or write on here, but also write on the board. Okay? Now, the place to go to. Now, if you read the instructions here, and it's well worth a read, folks. How many people left? Just one or more than one? Just now?
Oh, just one.
Just one? Okay. Who was it? Okay. Oh, okay. That's Ishmael. Okay. All right. Here we go. Now, if you look at the first page here, this is page 329. It has some definitions here, and you'll see these are very similar to the ones we had in the text. Definition of a little bit on rocks, but mostly minerals. Okay? That's in the first part. The next part has materials, and it talks about a mineral collection, streak plate, this kind of stuff. We're not doing this. Okay? What we're doing is getting the information, but we're going to get it off the internet. Okay? So what you're going to do is go to a website. Now, this won't have all the things you need, but it'll have most of them. And this website is http://webmineral, WEBMINERAL, not with an S. Do not put an S on it. .com. Okay? And for the very first one, you can put a /data and then do another /calcite. That's the first one on your list, CITE. That gets you right to calcite. And from there, you can figure out how to get to the rest of them. Y'all know the internet way better than I do. Okay? So, what you're to do is go to that website. Okay? Find calcite. Okay? Now, on your thing, the procedure, we're not doing it the way they said, but it describes what they mean by color, what they mean by streak. This follows exactly what we did in the text. What they mean by hardness, and they have Mohs hardness scale here, just like you had in the text. Cleavage, fracture, luster, density, and other properties. Now, for other properties, the one I want you to do is density. Okay. On your chart, you'll see there's 6 columns. Okay? Color, luster, streak on one page, that's 332, and then hardness, cleavage, fracture is in one column, and then they say other. Rather than other, you write density. Number 7 on 331. That's the best, the most important property to have and to know. It tells you the most information, and yet they left it off the table. So where they have other on page 333, the last column, you write density. Understood? Okay. So get to the website, okay, find calcite, and then start looking for physical properties of minerals or something like that. First one who finds it, and you'll start seeing. You'll see these very things: color, streak, color, luster, streak, hardness, cleavage, fracture, and other, all listed somewhere in a table there. Has anyone found it yet? Under physical properties, exactly. Okay. Now, calcite may list a bunch of colors. If they do, just pick the first 2 or 3, 4, however many you can easily, comfortably write in that first column and write them down. You don't have to list them all, but just list some of those colors. Have you found it yet? Any of you not found it? Again, this is the lab. Work with each other. I should get up and walk. This is opposite. Physical property. Are you in webmineral.com? Yes. Let me see it.
I got calcite.
All right.
Webmineral.com. Oh, you just type in your mineral property. So then,
Click on one of those.
where it says other, we put density in its place, right? And then you
Where it
click
says
on
other,
general information in its place. Do you see
Huh?
it? Put that in.
See right here?
Right.
First you click this.
Now, what we're looking for first is calcite. Now, what I'm used to seeing is when they're alphabetical. I don't see these alphabetical.
Click and scroll down.
Back
Go, and then you just find the different stuff that's looking for, like color, density, like all of like this. Right.
Go back up to your webmineral.com. Okay, try it again. Yes, that's it, exactly. So if you can have me. Everybody found it, found somebody who has found it.
Do we have to put like every single color?
Okay, I just went through that. I said write the few, what you can easily fit in that block, the top few, and stop when you fill the block. Okay? You don't have to put them all, but put a few. What's that? Do we have a test today? No. I said that at the beginning of the class. Is this alphabetical? Why don't you start with C for calcite? Okay, great. Okay. On the cleavage and fracture, okay, if you read what it says about cleavage and fracture on page 331, cleavage is the tendency of a mineral to break along smooth planes. Cleavage occurs in parallel planes in some minerals and in one or more directions in other minerals. Sometimes cleavage is perfect. Other minerals have indistinct cleavage. Okay? So they'll sometimes have a bunch of numbers, sometimes say perfect, sometimes say indistinct. But notice there's a slash in fracture. Fracture, minerals that do not have cleavage may show fracture, an irregular broken surface rather than smooth planes of cleavage. Some minerals have a distinct way of fracturing, others such as conchoidal fracture or obsidian or quartz. Conchoidal fracture is a breaking along curved surfaces like a shell. So basically, your minerals, most of them will either have cleavage, and if so, write the cleavage information, or they will fracture and then write the fracture information. If they have both, put a slash between the two, and just put a couple of things about each, like perfect or indistinct, or the numbers they show, and the fracture, conchoidal, or whatever. So sort of put a slash, just like you see the slash on the table. You see cleavage slash fracture. So put a few terms about cleavage slash a few terms about fracture. Okay? Now, here's another thing. As you go down your mineral list, you will find some of these do not have a mineral in the table at webmineral.com. I'm trying to remember, I can't recall for sure. I'm thinking maybe limonite, feldspar almost for sure, hornblende maybe, bauxite possibly. There are a few of these you will not find on that table. If you run into that situation, then go to somewhere like Google or some search engine, type in the name that's given here, and they will give you some mineral names. Take that mineral name back to this table and do that. And when you do that, like if it was feldspar, let's take bauxite. And bauxite, I don't think you'll find on the table, at the website. And I believe you'll find goethite if you Google it. And if you can find goethite in the table here, then write goethite over bauxite and give me the information for goethite. See, bauxite is an ore. That's aluminum ore. It's not really a mineral, okay? One of the ores of aluminum is goethite. There are many others. Pick any one of them when you do your Google search or whatever kind of search you want to do, and then put that one in. Write the name above the, like bauxite, and tell me which mineral you're writing about, and then start doing the color and everything else about that. Does that make sense? So as you go down, you'll find some of them are not in the table. If so, ask me and I'll tell you again how to do that. Okay. So for folks at home, if you're trying to do this at home, let me write down what I just said. This is for folks who aren't here today. It's http:// webmineral, webmineral.com. Don't put an S on there. That takes you to a different website. And then you can do /data and /calcite. And that gets you to the first one. And then from that point on, you're looking for physical properties of minerals or something like that, and you'll find the tables, and it'll have just about every one of these on it. Okay? It'll have something about color, something about luster, something about streak, something about hardness, something about cleavage and or fracture, and then the other will be density. Okay? The other column on page 333, you write density. Now, density technically will always have units, probably grams per cubic centimeter. If you see a number there without the units, then that is specific gravity. Same. So you could put density / specific gravity if you want to. Or you could just put density and list it. Now, there's one other thing. Once you finish the table, then go back to page 331 and you write the results. And you only need to write a sentence or two. It says, was the purpose of this lab accomplished? You can say yes or no. Why or why not? 1 or 2 sentences will do. Okay? So that is a blank, a question. Don't forget to go back and do that at the end. Huh? I can't hear you. Okay, got it. All right. Then if there's no more questions, I'm going to pause this. But when you have a question, bring it up, and I will turn back on. Remind me to turn back